Hey guys, we're going to do a little investigation about weight. Now, you already know about the force of gravity, and the force of gravity is your actual weight. And so the force of gravity, an equation you learned in the last lesson, Fg being the force of gravity equals mass times the acceleration of gravity, Fg equals mg. Now, what that means is for your actual weight, how much you actually weigh, the force of gravity, the only way you could possibly change it is if you gain mass. I don't know, maybe eat a donut, or if you go to another planet where the acceleration of gravity is different than here on the surface of the Earth. So you go to Mars, you go to the moon. I know that's not the planet, but you go somewhere where the acceleration of gravity is actually different than what it is here on the surface of the Earth. But something weird happens whenever you get on an elevator. It ends up occurring on a roller coaster as well. You get on the elevator and you go up to another floor. Maybe you're coming back down from a floor, back down to the ground floor, maybe from the second floor back down to the first floor up. And even though your actual weight doesn't change, what you feel is different. Because whenever you are accelerating, your apparent weight, what you feel, you might feel lighter or you might feel heavier. Now, your apparent weight is associated with what we call the normal force. Normal force is how hard the floor has to push back up on you to keep you from falling down through the floor into the middle of the earth, so to speak. So your apparent weight, normal force, your actual weight doesn't change, force of gravity. We're actually about to go to the school elevator here in a second and take a look at that. We're going to use this setup right here. This is a 50-gram mass. This is a spring scale that goes up to 1 Newton. Now, a 50-gram mass here on Earth, 50 grams, that's 0.05 kilograms times 9.81, the acceleration of gravity, about 10. It should read somewhere around 0.5 newtons, and it does, right about 0.5 newtons, just slightly less because 9.81 isn't exactly 10 there. So it's reading its actual weight right now. We're going to take this on the elevator, and then we'll go from the first floor up to the second, and then from the second floor back down to the bottom, and we'll see what happens. Hey guys, all right, we're here in the school's elevator. We're on the first floor. I'm gonna take us up to the second floor and then back down. I got a nice zoomed in shot for you of the spring scale so you can see what happens. What you're gonna notice is whenever I hit the 2 button and we start going upwards, we're gonna accelerate for just a second. And whenever we're accelerating upwards, something's gonna happen to the spring scale. Either the mass is going to seem to be heavier or lighter than it actually is. And then it'll go back to normal as we hit that constant velocity on the way up. But whenever we get to the second floor, we have to decelerate to stop. So we're actually going to end up slowing down. And as we slow down, decelerate, you're going to notice a change on the spring scale. Go back to normal, and then we're going to end up reversing the process. We'll accelerate downwards back towards the first floor. There'll be a change until we hit the constant velocity. Back to normal. And whenever we get to the bottom, you'll notice that we have to slow down to stop. The mass is going to look heavier or lighter than there too. All right, here we go. All right, we're on the second floor. Now, there was a little bounce whenever we were getting, whenever the elevator was jiggling into the first or second floor, so to speak. Here we go back down. Back at constant velocity. We're about to hit the bottom.
First floor.
And now we're there. Hey guys, what you should have noticed there is there were 4 spots where the apparent weight, what's being read by the spring scale here, was different than the actual weight. Now, whenever we were at rest, or whenever we were traveling at constant velocity, the apparent weight, what the spring scale read, was exactly the same as the actual weight, mass times 9.81, Fg equals mg. But the accelerating up from the bottom, well, whenever we were on the way up and we were getting to the second floor, we had to decelerate to stop, and then the coming down part too, right, accelerating downwards, and then whenever we were at the bottom, decelerating to a rest, the weights changed a little bit. So can you explain that? Try using the terms inertia, and of course use the terms apparent weight and actual weight. Maybe some free body diagrams would actually help explain that. Maybe 4 free body diagrams, one for each case, where you've got the force of gravity, Fg, going down, and the spring force, F sub S, if you will, going up. And of course, whenever you're standing in an elevator, the spring force going up would equate to the normal force if it was the floor pushing upwards. So see if you can construct an explanation.